today we would look at how to really go about training a neural network. So in this video, let us discuss about how to babysit a neural network. So really we are going to study about how to train a neural network because we have seen the basic building blocks. So we have put them into a network and we have trained on the MNIST data set. So the data set which has hand labeled data, and we will look at how to set the hyperparameters. So how to start off? What are the things that we should look at? And then how to finally choose the various hyperparameters that are required for the network. For example, the learning rate, the weight decay, and so on. So let's start as we have done the previous time. So we are again doing a neural network from the scratch. So the only Python library we will use is NumPy. So we import NumPy as NP, and then we create the linear class or the fully connected class or the dense. We can also call it the dense layer. So as you know here, we have a fully connected layer where every neuron in the input is connected to every other neuron of the output using a weight matrix. And then we have bias, which is the size of the output. So this is exactly what we are doing here. We have the class defined here. The class constructor takes in the two parameters, the input size and the output size. So input size is the number of input neurons and output size is the number of output neurons. So what we are doing here, we are creating a weight variable, which is a member variable. And this is of size, in, size, and out size. And at the same time, we are initializing it in the range of 0.01. Next, we create the bias. As you know, bias is of output size, which is the number of output layers, and we initialize it by 0. We then create a member variable called params. This is the list, and this list contains the learnable structures that we have in our class. So self.w and self.b. And then we also have the gradients with respect to the weights. The gradients with respect to the bias and gradients with respect to the input, we all set. We have the forward function which essentially takes the input. What we do is we create a member variable which remembers this input because we then need to use it in the backward, right? Then in the backward pass, we use it here. And we then compute the output simply by multiplying the input with a weight and adding the bias. So this is the linear aspect of it. So the output is nothing but W into X plus B. And we return the output. We then have the backward function. So since we can modularize each of these modules, right? So we can have a separate backward function being called for each of these modules, such as the linear layer, the ReLU, the cross entropy, and so on. And here, as you have seen earlier, we know that the gradients with respect to the weights is nothing but the weights multiplied by the inputs multiplied by the gradients coming in from the next layer, right? So all we do is we do a multiplication between the inputs transposed and the gradients coming into the next layer. And this happened to be the gradients with which we will update the weights. Similarly, the gradients with respect to bias is the summation of gradients coming in from the next layer. So I think till now it is clear to you, right? So we do a dot product between the gradients coming in from the next layer and the weights of this layer transposed, and this is the gradient input. This is the gradients which you will pass to the previous layer, and finally we return. So this is a norm that we follow. So we always return two things. We return the gradients which need to be passed to the previous layer, and also we return the gradients with respect to the parameters of these layers. Right, so I think this part is clear to you, right? So the gradients are grade W and grade B, and this is also like gradient. So this, as you have seen earlier, is how we define the fully connected layer or the linear layer. Next, we define the ReLU, the rectified linear layer. So here again, the constructor takes in no arguments. We have we have two state variables. So self.param, since ReLU has no params, it's an empty list and it will remain empty, and the grad input is something that we are setting, right, which we will populate later, right? And then we have the forward function. The forward function takes the input x, and as you know, the ReLU simply takes the output as the maximum of 0 and x. So what it means is you can take your input and you only pass that thing greater than equal to 0. So anything which is less than 0 becomes equal to 0, and this is what ReLU does. So the rectified linear unit. And similarly in the backward pass, what we do is we have the gradients coming in from the next layer, which we call next grad, and the gradient with respect to whatever is coming in from the next layer. As you know, what we are doing here in these two lines is we are killing the gradients for whenever the input was less than 0, right? So that is what we are doing over here. So suppose the output of so the input let the input be 2, 3, 4, and 6. Suppose we have a ReLU here, so you know, okay, so let me write that example. Okay, so whenever we use that ReLU, what will happen? What will be the output now? Everything which is greater than 0 will be the same number, but whichever is less than 0, that becomes that becomes actually 0. Say for example, -2, 3, 4, 6. Okay, so I just give it to ReLU, right? So what will happen now? So 3, 4, 6, this will become 3, 4, 6, and this -2 will become 0, because this is what the function of the ReLU is, right? And so this is what we have to understand over here, right? So what would be the output? So whatever we give, what would be the output? So everything which is greater than 0, right? So 3, 4, and 6 will go out, but -2 will become 0, right? So this is the forward pass. Now let's say during the backward pass, we are getting as we know, this is the backward pass. In the backward pass, what will happen? This is the next grad, and suppose the next grad is say -9, -6, -9, sorry, 3 and -14, right? So let me write it down, right? So in that case, when you apply next grad, what will happen? What will go there? So that is what we have to think about it, right? So what will happen now? Say I have -6, -9, 3, and -14, right? So here I had -2, 3, 4, and 6, right? So this is nothing but next grad, right? Next grad, right? So what will happen now? So this will become 0, and simply we pass it, right? So this is what we would look: 0, -9, 3, and -14. So now I hope this is clear. So this is very simple. ReLU acts as a gating unit. You have the forward path where it kills everything which is less than 0 during the pass. So wherever you kill, you do not pass gradients for that neuron, and you pass it everywhere else. And wherever it was less than 0, you make the gradient equal to 0. So now softmax is again something which you know. So it's simply exponentiating it and then dividing it by the sum of all the exponentiations, right? So it makes peaky, and also it makes it a probability distribution. So the sum of when we get this output, if you sum up this vector, it will be equal to 1, because it is the probability distribution. Now we have also seen this in the past. So this is the cross entropy loss. So here you can remember, I mean, so the cross entropy loss, you should remember that the way it is implemented here, we are getting the score. So the score, so this is the output of the final layer. This is before the softmax. The softmax is here inside the cross entropy loss. Okay, so we get these scores from the last layer. We then this is essentially so this is the scores. This is the target of the ground truth, right? So we will first convert this into probability. So self dot p is the probability, right? So this is the scores of the last layer. This is the probability, and then what we do, we are so we have this m, which is the size of the batch, and all we are doing is, so we have to do this because we are dealing with the batch, right? And then we are averaging by the batch size. But if you don't have this batch element, all we are doing is we are simply computing the cross entropy loss. And yes, so the loss is nothing but, as you know, for whichever is the correct class, right? So suppose let's again do this with the quick example. So let's suppose we have this as the output. So we have some output, say, and we have the let us look into the class also. So this is 0, 1, 0, 0, right? And whichever is the correct class, we simply do a negative log loss, right? Say so minus log, right? So this is the probability, right? So now what is the perfect loss? So suppose you got exactly 1 here, and then your loss will be 0. This will happen when your network is absolutely confident that this is the class, but in practice you would get something like maybe 0.9 here, it's not exactly the same one, right? So which will be the output of the cross entropy, and this is what we get as loss here. So this is also simple. And as you may also remember, that the backward of cross entropy is also very simple. All we do is we simply subtract 1. So wherever we have wherever we have our input, we have our targets. So we again create cross entropy. That is also very simple, and all we do is simply what are we doing over here? We do is simply subtract subtract 1, right? So wherever we have wherever we have our input, we have our targets, we again going to create we put the extra softmax. So here we call it so here we can look it over here, right? So we will wherever was the right class, just we simply subtract 1. And so again, I mean what we are doing is okay, so let me explain the same with the help of an example, right? Fine. So let me explain with the help of an example now. So this is the output of the softmax, right? And wherever is the correct class, we simply subtract 1 from here, and everything also remains the same. So we subtract 0 from every other place, we subtract 1, right? I hope that is clear, right? So that's clear. So now we don't really need pandas. We can, if it is required, we can use pandas. Otherwise, it is not even required. You can also use pandas. Using that also, like in case if you are using any data set, if you are loading into it, you can use it, right? Right, so that's what I wanted to tell about that. So I'm going to use here as Keras data set. So Keras, for example, it has data sets, and MNIST is already contained in Keras. So we import MNIST from the Keras data sets, and we will also use the utils. So we also import keras.utils as nputils, and then we call mnist.load data. So mnist was loaded, right? So mnist.load underscore data, and this gives us these 4 elements, right? So these 2 tuples, and in these 2 tuples, so this is the training images, the training targets, the test images and the test targets. So here what we are doing is we are then flattening our training into one big vector. So I mean, if you look at the size of this, it will be something like 60,000, 28, 28. And what we are doing here is 28 into 28 is 784. So we have a square image, and we are flattening that 28 cross 28 into one long 784 long vector. right? So now, I mean, if you simply look at this, also what you might have seen was this would be of size 60,000, comma 28, comma 28, right? And this reshape, we are converting this part into 784. So this is simple. We do the same for the test set. The test set has the same dimension, but we have 10,000 examples here. And we again flatten it out. So we print the shapes, and if you look at the shapes of this, and it would exactly be this. And this as can be seen here, right? So we have done reshaping so that it is easier for us to train. We also want to normalize it so that it is in a more palatable region. And so you can normalize in between 0 and 1. You can also normalize it between -1 and 1. We are just going to normalize between 0 and 1, and you can print the maximum of it, or so it ranges from 0 to 255. So otherwise, so that's what we have done over here. So here we are normalizing between 0 and 1. And size, so then we are also printing the size of the target. So the targets are nothing but labels. So for example, the first image may have a label 4. The second image may have a label 6. And so we have one label for every image, and thus we have 60,000 training labels and 10,000 test labels. And then we create these two variables called x_train and y_train. X_train has the training images flattened out, and y_train has the training labels flattened out. Similarly, X validation and Y validation has the testing, labels, no flattening out in labels. It is simply one number per image. Now here we try to visualize it. So we call matplotlib inline so that we are able to visualize within the notebook, and then we import PLT from matplot. So we import pyplot as PLT, right? Fine. So matplotlib.pyplot as PLT, we have a figure size 10, 1. So this is how, so in inches, it should be 10 inches wide and 1 inch tall. And then we loop 10 times, and then we call subplot. So subplot basically says that, okay, one row. So the size of the plot, will be 1 row and 10 columns. So this is what this 1, 10 tells us. It could be also like 10, 10. So it will have 10 rows and 10 columns, and then this is the number. So it will go like 1, 2, 3, 4 up to 10. Then 11, 12, 13, 14 up to 20, and then all the way to 100. So here it will go from 1 to 10, right? So it goes from 0 to 9. So here we go from 1 to 10. And within each subplot, we plot 1 of 4. So we plot the first 10 training images. So we first plot the first training image. We again have to reshape into something that we can visualize, because we have converted into the 784, and I use the gray color map. Because if you don't use this, it will display it in a heat map format between, so it will be a blue-red image. So that's why I have used a color map is equal to gray. So we use a color map gray over here, and we choose the axis off. And finally, once we have done that, we show it. So this is not still, this is still in memory, and this is where it dumps onto this notebook. And we also then print the labels for each of the images using this print command. So we are simply this array, and we are simply printing the first 10 elements. And as you can see, this makes sense. So these are the input images, and these are the corresponding labels. These are the input images, and these are the corresponding labels. So the first image is 5, and the label also says it as 5. So this makes sense, and this is the first step that we need to do when we are doing machine learning. We have to visualize our data, we have to visualize our training data, we have to visualize our test data. If we are dealing with text, we should still do some sanity checks where we print a word and we print the corresponding label. If we are dealing with speech, we should still manually hear it, and then we should hear the speech segment, and then we should also look at the corresponding label. So this is the sanity check. If you take garbage data in, you can only expect garbage data out, right? So this is the first thing we should always do. It so happened many times that we have simply loaded incorrect data. Maybe there was a problem. So maybe started off with one and then our algorithm just doesn't work. So this is the first step that we need to do. Now we can load and visualize the data. We have loaded and visualized the data. So we can move on to the next step. So this is something again that we have gone over. I'll just so in the previous just let us discuss about this in a while. Right, so this enables forward and backward propagation of the entire network. So you should note that how this class enables us to add layers of different types and also helps in currently passing the gradients using the chain rule, right? So we define a class, the constructor takes in the last function. Here it happens to be the cross entropy loss. Remember, we have defined the cross entropy class already, right? So we have set the default mode to train. So we define a bunch of state variables. So we have state variables, parameters, we have state variable layers, where we will add our future layers. So this will be the parameters of the entire network. So the last function happens to be the cross entropy. So we put it in a state variable. So once we are done calling the constructor, we have the gradients and we have the mode, and now we have a class function add layer it takes in. And now we have variable of type of variable layer, and this layer is one of these classes. So the layer can be easy, the ReLU layer or the linear layer for our case. And what we do is we have this list, remember, and it simply appends it with the layers. Right, and if this layer has any parameter, so the layer will always have params. So the way we have defined it, even if we do not have any parameters, for example in ReLU, layer will have an empty list params. So this is the reason we had to do this. So we call this, so we have this params, and though we don't use it, so that it doesn't throw us any error saying no. So whenever we call it, if there are parameters in that layer, it will add it up to the class variable params of the neural network class. So by the end of this, the list should be populated with all the parameters and of all the layers in this network. Then we have this function called forward through the entire network. So what does it is, so for the, and then suppose this is the first layer. So this is the input, this is the input to the entire neural network. So you maybe know the 784 long vector. So it puts onto the first layer, it calls the forward function of this layer. So it may call as the forward function of the linear class with the input. So it gets some output. So we overwrite this input with this output, and then in the next step, suppose now this is layer 2, we set the output of the second layer. Right, and we keep on doing this for number of times we have layers in this network. So suppose we have 4 layers network, then we do it for 4 times, right? So in our case, we have a 2-layer network. So then finally we return the output of the entire network, which is again yes, because we keep on writing that, right? This is backward, and backward essentially does the backward pass of the entire network. And look at the beauty of this function. Though backward is fairly complicated if you want to do everything manually, but since we have modularized it, and since we are using the chain rule, we can simply call backward for each of these classes. So the only thing that we need to do here is to remember that we have to call backward in the reverse way. So backward takes the gradients of the next layer, and all does is it so it passes it into the backward of the current layer. So now we will transverse all the layers in the reverse order, and we will pass it the gradients coming it from the next layer. So backward, as you remember, will give us two things. It will give us gradients with respect to the parameters uh, and the gradients which need to be passed to the previous layer. So this may be empty. When it will be empty? It will be empty for layers where we do not have the parameters. For example, ReLU. So for ReLU, this gradient will be empty. But we will always anyways have this and see that we pass this back into this when we loop over this the next time. So what we keep appending our gradient vector with the gradient which comes in for the parameter. So since we have self.params and we have self.grads, and also note that both of them will be of exactly the same size. So later what we will do is we will update the self.params using self.grads. So train step is the function where it actually does the backward. So train step is still not actually updating. Updating happens here, but this is where it keeps everything ready, right? So this is where it does all the loss calculation. It does all the gradient calculation, and then this update function simply uses the gradients and the parameters to do the final update on the parameters. So what does this train step do? The train step takes in two variables, the input and the output. It forwards, so it calls nn.forward. So this is the entire network. So this is the output of the network. And so this is the output of the network. So since we call it with this input, so using this output, it computes a loss, right? So it computes a loss and we are doing the weight decay or the L2 regularization. So it looks complicated, but essentially it is looping over all weights and it is adding this lambda. So this is the L2 regularizer for this network. So L2 on the weights, and this loss is simply the loss, right? It is simply the loss. So it calls cross entropy forward with the output of this layer and the ground truth, right? So we have the target, the ground truth. This is cross entropy. When we call it forward the cross entropy with the output, and the target we get the loss, and we also add L2 on the weights. The gradients which we need to be passed to the previous layer is again the loss. So the backward of the loss function here, and the backward of the L2. So backward of the L2 is pretty simple. It is simply, so if we decide that the L2 turn is 1/2 lambda norm of W square, then this will be lambda times W, right? So this is what happening here. And then is the gradients which we need to pass to the previous layer. So this is the gradients with respect to the weights, and we call it backward or the entire network, we get the gradients, right? So if you remember backward here, finally it returned the gradients. So we have to call backward with the gradients coming in from the loss function. So we have our cross entropy gives us the gradient which need to be passed to the last layer. So this is what we have got here. So we pass it to the last layer, so that we call backward, which takes next grad. So we have next grad from the backward of the cross entropy function. So we put it here, and then we get gradients for each parameter in this network, and that is what train step does. So find how we have got all the gradients of all the parameters at work. No, we still haven't updated these parameters. We will do this in the update step. So train step essentially keep your gradients ready so that we can use it to update the parameters in the network. Now we have 3 or more helper functions, and these 3 helper functions are the predict function, the predict score function, and the clear grad param function. So the clear grad param function is the easiest of all, and this is essentially clearing the gradients because we don't want to keep adding to the gradients, right? So once we have done one backward pass, we have cleared the gradients, and this is what we call here in the backward function of the network. So once we have to clear the gradients from the previous step and then add the new gradient which come out from the current backward step. So this is what clear grad params do, right? So predict function is nothing but final answer of the network. So what we are saying here, you have input, you pass it to the network. So we have our input which we have put in here, you pass it to the network. So you call the forward, right? So you get the output of the network, you put this output into softmax, and you get the probability distribution, and then you call the argmax of the first axis. So this essentially gives you the label for the class. So then it gives you for this image, it is label 1, label 2, and so on. What could you have done before, right? So you could have removed this function, no, because the softmax is simply transferring your scores to a probability distribution. But if you call argmax also on this here, it will give you exactly the same answer in terms of the label.